let's now see how we can avoid the ABA problem. And the problem really was that a pointer can be reduced and compare equal to another pointer, but the context of this pointer is not it's not valid any longer, as we saw in the previous video. So what we can do is to, in addition to an address, we can also add a serial number, so that whenever we create a new node, we also get a new version, so to speak, just a number that makes this node unique, meaning not only the address but also the use of this address. Okay, so what do we do? Well, we have a struct called a pointer, and it contains the pointer as in the previous version, and we also have a number type long. That's a 64-bit number usually. Okay, and now the stack has it's an atomic, not only node pointer, but it's an atomic pointer. It's not a pointer to a pointer. That's not what we want. We just want the previous pointer, but with the uniqueness. Okay, so what do we do? Well, we need this to keep track of a new serial number, and we can see what happens at a push initially. Okay, as usual, we create a new node, and that will be the same as previously. I mean, we can, well, it's exactly the same. And what we do more, we take the old value of the top of the stack. That is what we will use as the parameter to atomic compare exchange. I mean, that is the one that we will compare with and also get updated. Okay, and then we have a new node, and that is a pointer, I mean this type, and it points to the new node that we just created and gets a unique number. Okay, and then we set new node next to the old node. Okay, and why do we do that? Well, it is to link our newly created node to the current value of the top of the stack. Well, possibly the current value. Somebody may have changed it. Okay, and then we do the atomic compare exchange weak, and it checks if the top of the stack is equal to old. And if it is, then we will, this function will update the top of the stack to our node. To this new, to the pointer. And it has the newly created node with a unique number. Okay, but if it's not the same, then old gets updated to the current value of top of the stack. So what do we do then? Well, we update our node next, so that it will point to the current top of the stack. So that's why we are iterating. I mean, that's what we need to do when we iterate, because we want our new node to point to the top of the stack. But we want our new node, I mean this new variable, to have to keep its current unique number, because that is what we want to eventually give to the top pointer of the stack. Okay, and then to the pop, it's similar, and we get the new value, and we well, we check if it's an empty stack. Otherwise, we set the new node to the next. I mean, we want to set this to that the top of the stack should be pointing to our new variable. Okay, so we try this, and if this current value of the top of the stack is now equal to what we just read, then we set the top of the stack to our node, meaning this new number and the next as expected. Okay, and then we can take the key and we can free the node and nothing bad will happen. So let's see if this works better. Okay, okay, we can use 80 threads, and well, this one is slower because now the atomic compare exchange is using not only one 64-bit value, but it uses a struct. So let's reduce the number of tests. Okay, let's see what happens. Okay, not much, but let's see if we why not. We can do many fewer, and just to get a feeling for how long time this takes. I know why. we are using the wrong file. Okay, as you can see, when I press V in escape mode, I run make, and it uses the wrong file. So let's update the make file. It should be like that, and now it should work quicker. And let's add, okay, let's do 80 threads with this view, and it is quicker. Let us add some more numbers and some more tests. Okay, this takes a lot of more time. It takes too much time. Okay, so it would be, I mean, too slow to look at. And these tests, well, what do? They just have, in this case, 80 threads. One is doing the pushes and the other doing the pops. And they just check that the sum of the values that were pushed is equal to the sum that was eventually popped. Okay, so now it works without crashing. Okay, and for the exam, this is grade 5, and this stack you should perhaps not 100%, but quite thoroughly understand what's going on. Okay. But the queue is more complex, and there will be a remark about that in that video. And we will look at the queue next.